All right. Hello, everyone, and welcome back to Calculus. So today we are going to be talking about related rates. So this is really talking about how rates of change within a situation can be related to each other. So these will be things like when you're blowing up a balloon, the radius is increasing, so is the volume. And can we relate the V prime to R prime and so forth? And so we are going to be seeing a few different examples of doing this today. Oh, there we go. All right. So the general steps to this is we're going to need to sort of figure out which variables are present and clearly define what notation we're going to be using for each. A lot of times it's going to help to draw a picture to sort of see visually how the variables are going to be related to each other. We're going to start by writing down any sort of known quantities or equations that we can figure out from our picture or from our word problem. And then the last step, which is the main step, is less, how do I want to say? It's going to kind of vary each time in terms of what exactly we're going to need to do in order to finish the problem out. So the way that I like to say it is follow your nose. There's going to be sort of hints in sort of all of the known quantities that we have to help us get towards the quantities that we want. And so we're just going to kind of go back and forth and keep looking at what we have, what we want, and just kind of follow our nose, trying to figure out how to get to what we want. So let's see an example of this. So example one, we have two planes that are leaving an airport at the same time. Plane one is going to fly directly east at a rate of 520 miles per hour. And plane two is going to fly directly north at a rate of 480 miles per hour. What we're being asked to do is find an equation for the rate of change of the distance between the planes after t hours, and then also interpret this amount when t is 2. Okay, so first of all, it seems like the relevant variables and sort of amounts that are going on are going to be, let's see, so maybe kind of go back and forth between my picture step and my variable step. All right, so I've got a plane that's flying directly east and a plane that's flying directly north, and they both left my airport at the same time. And plane one is going this way at 520 miles per hour, and plane two is going this way at 480 miles per hour. And then the question was about the distance that's between my planes. So it seems like the relevant variables is t is going to be time. It's measured in hours. Let's say P1 of t is the distance traveled by plane one by time t. Remember, plane one was going this way. So for example, at time 0, plane one has gone 0 miles per hour. Or 0 miles. They're just now leaving the airport. So P1 of 0 would be 0. But after 1 hour, since they're flying at 520 miles per hour, P1 of 1 is going to be 520, and so forth. Okay. Plane 2 at time t, that's going to be the distance that plane 2 has traveled. And so then this last thing that we care about is the actual distance between my planes. So distance between the planes at time t. It's very important that you actually sort of directly write this out, especially since we aren't given sort of the notation for these things, so that your reader actually understands what the heck you're doing in the rest of the problem. We've made it very clear what we mean by all of our variables. Okay, cool. So we've figured out our variables. So the next step is to take all of our variables and kind of write down all of the things that we know about it and so forth. And also it's going to help to sort of update our picture. So my picture, I'm going to think about this length of how far I've traveled. Again, it's P1 of t. This length is P2 of t. This length is d of t. And let's see. Okay, so we're told that plane 1 is flying directly east at a rate of 520 miles per hour. So as I kind of talked about earlier, that says that P1 of t, it's going to be 520 t. So we start out having traveled 0 miles, and then we travel 520 miles for every hour. And similarly, so that was this yields to this. So that is a poor choice of color for that. So this information gives me that equation. Similarly, I could say that plane 2, the distance it's traveled at any given time, is going to be 480 times the number of hours that we've traveled. Since we're traveling at 480 miles per hour. Then let's see, what else can we find in this word problem? So the last 2 sentences are really about what we're trying to find. So the only other thing that I see that's like a possibility of something that could be translated into an equation is the fact that our planes leave the airport at the same time. That's already kind of gone into this. We know at time 0, both of them haven't gone anywhere. So P1 of 0 is 0 and P2 of 0 is 0. So that kind of went into those equations already. So those are the things that I can get by translating my word problem into, into equations. So these are 2 of my known things. And then it also helps to look at my picture. So I know that for my picture, I've got a right triangle. And so I could apply the Pythagorean theorem to relate my d of t, p1 of t, and p2 of t. So another thing that I know is that if I take d of t and I square it, then I get p1 of t squared plus p2 of t squared. And that's all that I can really see between the picture and between my word problem. That's kind of all that I can think of in terms of things that I know. What I've been asked to find, or what I want to know, is the rate of change of the distance between the planes after t hours. So distance between the planes was d of t. So the rate of change is going to be d prime of t. So I want an equation for that. And we also want to interpret this amount when t is 2. So specifically also going to be thinking about d prime of 2. Okay, cool. So that is sort of the next thing, or the next steps that we need to do is think about our knowns and our wants. Change this maybe to just a different color to make it a little visibly distinct. Okay. And so let's see, then our final step is going to be trying to get from our known amounts to our wanted amounts. Okay, so I want d prime of t. I know this equation that involves d of t. So probably it's going to help to take the derivative of that thing. So let's see, d of t squared was p1 of t squared plus p2 of t squared. So if I want to find d prime, I'm going to go ahead and take the square root of both sides of that equation. So I can say that d of t is really the square root of p1 of t squared plus p2 of t squared. And like I said, I want to take the derivative of this. So I'm gonna just write that instead of thinking about it as the square root, I'm gonna think about it as to the 1/2. That way I can see my chain rule a little easier. So based on this, in general, d prime of t is going to be 1/2 times, plug in my inside function again, so p1 of t squared plus p2 of t squared to the minus 1/2. That's, so as far as the chain rule goes, that's my derivative of the outside with the inside function plugged in. And then I need to multiply by the derivative of my inside function, which is my p1 of t squared plus p2 of t squared. And those are, again, actually going to be chain rule things. So the derivative of p1 of t squared is going to be 2 p1 of t to the first times p1 prime of t plus, again, derivative of p2 of t squared is going to be 2 p2 of t times p2 of t prime. Based on chain rule on those pieces. And let's see, I can actually fill this out even further, right? Because I really want d prime of t. I want this as a function of t. So I don't really want these p1 of t's and p primes. I don't want those. I really just want functions of t. But remember, I knew what p1 of t was and what p2 of t was. So I can go back and I can plug those in. So d prime of t is 1/2 times p1 of t squared, so that's 520 t squared, so 520 squared t squared plus p2 of t squared is 480 squared t squared minus 1/2 times 2 p1 of t is again 520 squared, or is 520 t times p1 prime is just going to be 520 plus, this is all in parentheses, 2 times p2 of t is 480 t times p2 prime is again 480. So just a little. All right, so in total, we end up with these problems are long. In total, we end up with 1/2. Really, if I want to make this kind of write this all nicer, I'm going to take that negative 1/2 and I'm going to move it into the denominator. So 520 t squared plus 480 squared t squared, square root of that, and then let's see, let's simplify that down a little bit. So pulling up my calculator here. So 520 squared plus 480 squared. It's going to be 500,000 in 800. And then let's do the square root of that. And it's not a super nice number, so we'll just leave it as that. So really this is, I could pull out my t squared out of my square root and just get a single t. And then I'm going to be left with the square root of 500,800. Okay, so that's just cleaning up this portion so far. And then I end up with My 520 squared plus 480 squared, so that was that 5,800 times 2 in my numerator. So, oop, so 1,000,000 1,600 T. Okay, so when I clean all of this up, when it's all said and done, I get this amount, which of course can actually be further simplified by recognizing that my t's divide out. And also my 1,000,000 can be divided by that too. Really just getting this. I'm getting square root of 500,800. For any given time t, d prime of t equals that square root. Okay, cool. So that was the first thing that we wanted to know, was what d prime of t equals. And so from all of this work, we have now said that d prime of t equals that amount. So in particular, it also asks us about d prime of 2 and interpreting that. So since d prime of t is always that, d prime of 2 is going to be that. And the way to interpret this is, so d prime is the rate of change of the distance between the planes. And we know that time is 2. So at 2 hours in, the distance between the planes is increasing by this many miles per hour, since it's a rate. Sort of instantaneously what the distance is changing by. Okay, so we have now answered the 2 questions that we were asked to answer. All right, so next equation, or next example, gonna do similar sort of thing. So we're told that a spherical balloon is being blown up at a rate of 3 cubic inches per second. Find the rate of change of the radius 10 seconds in. Okay, so again, sort of thinking about the relevant things that are going to go on. Our independent variable is going to be time measured in seconds. We can talk about the volume of the sphere, or the volume of the air, really, that has been put into our balloon by time t. So this really does rely on time. So this is going to be measured in cubic inches. We can also talk about the radius at time t. Going to be measured in inches to be consistent. Okay, and that seems to be all of our relevant variables. So we've given everything names that we needed to give names. So perfect. Then the next step, of course, is drawing our picture and trying to translate everything from our words and from our pictures into equations. So let's see. My picture is at any given time. I'm going to have a sphere. And of course, radius is going to be there. Volume is the total volume of the sphere. So if we remember back to our geometry days, something I could say based on my picture, so this is a known quantity, is going to be that the volume at time t is equal to 4/3 pi times the radius at time t cubed. Okay, that's one thing I know. Another thing I know, if I look at sort of translating the sentences in my word problem, is that my spherical balloon is being blown up at a rate of 3 cubic inches per second. So I could also say that v prime of t is 3. And since the volume of my balloon, it has to start at 0, I could also even, in fact, go further and say that v of t is really going to be 3 times t. My volume at any given time is just how long I've been blowing up my balloon times 3. So that's kind of all that I'm given. And then I do want to know what the rate of change of the radius is 10 seconds in. So really it's asking me to find r prime when time is t, or time is 10. Okay, so that is, as far as I can see, everything that I could write down in terms of my known quantities and my wanted quantities. So now we're at the step of following our nose, trying to get from these things that we know down to what we wanted, which was r prime at 10. Okay, so following my nose, really, I want something about r prime. At a specific time, sure, but like if we can find r prime of t first, then we would be able to find r prime at 10. And the only equation that I have that involves r at all is that one. So if I take the derivative of this equation, I might well see something that involves r prime. So that is what following my nose in this context means. So I'm going to do d dt of b of t equals 4/3 pi r of t pi times r of t cubed. So I'm going to need to take the t derivative of both sides of this equation. So when I take the t derivative on the left-hand side, I just get v prime t. And then on the right-hand side, let's see, my coefficients stay. And then I have to do chain rule on this r of t cubed. So I get 3 r of t squared times r prime of t via the chain rule, where my inside function was r of t and my outside function was t cubed. Okay, this is good. We wanted r prime of 10. Now I see something about r of t. So that's good. We're getting somewhere. Okay, so let's see. There's still too much other stuff going on though, right? Like I really want an equation in terms of t. So I want to get rid of this r of t and v prime t and really just switch those into equations in terms of t. So what can I do? Let's see. Oh, well, back to my knowns. I knew what v prime of t was. That's always 3. So I can replace that. So I know 3 is going to be 4/3 pi. Oh, that 4/3 and that 3 can cancel. So really, think of this as 4 pi times r of t squared times r prime of t. Okay. So again, just cancel those. Plugged in v prime being 3. And then I really want something for r of t. And it doesn't feel like I quite have that until I look back at my knowns. I realize I have these 2 different equations about v of t. So maybe if I combine those, I can get something. So again, I'm trying to think about finding an equation for r of t. I knew that v of t was 4/3 pi times r of t cubed. I also know that v of t equals 3t. So if I solve this for r of t, then I would have an equation for r of t in terms of just t. And so I multiply both sides by 3 over 4 pi, and I get 9 over 4 pi t equals r of t cubed. And so I can replace r of t by the cube root of 9 over 4 pi t. Okay, so in this, plugging that back into my other equation, that says that 3 over 4 pi equals, oh, sorry, let's not move that fully over yet. So 3 equals 4 pi times the cube root of 9 over 4 pi times t, that quantity squared, times r prime of t. And so at this point, I've got everything that I need to really get r prime of t as just a function of t. So let's just solve this final equation for r prime of t. So this says that r prime of t equals 3 over, 4 pi times the cube root of 9 over 4 pi t squared. That's for any given value of t. And so in particular, we wanted r prime at 10. So that just means we need to plug in 10 to this. So r prime at 10 is going to be 3 over 4 pi times the cube root of 90 over 4 pi, plugging in t being 10, squared. All right, and that is what we were asked to find, was what our rate of changes in our radius when t equals 10. All right, so this is, again, the general idea behind rate of change problems is you're going to have sort of multiple quantities that are all changing over time. So for example, in this problem, we had that the radius and the volume were changing over time. And then you're going to sort of look at everything that you know, look at pictures and so forth, and try to sort of follow your nose until you get to where you want to be. All right, fantastic. I'll see y'all next time.